Welcome to another conversation on sustainability. This one's a little unique. I'm joined by Brian Mazzeo and Sam Craven from Brigham Young University. Brian is a professor of electrical and computer engineering, and Sam is a PhD student who has led a project focused on helping us better understand and manage one of our most precious resources, water. And what I love about today's episode is that, yes, it's about agriculture, it's about research, it's about technology, but it's really about students who are discovering that, no challenge is too big, and meaningful change is something it's not reserved for someone else or sometime in the future, but it's something they can make happen today. Brian, Sam, welcome. Thank you so much for joining us. I'm really excited that you're here.
Thanks. Great to be here.
Thanks.
So before we get into the technology, Brian, I'd love to start with something you shared with me about your philosophy and approach at the university that really stuck with me. So you said, as a university, you think in terms of, the benefit to the world. How does that shape the kinds of research projects that you take on?
Well, I think that benefit to the world that we try to provide kind of takes multiple dimensions. One is certainly the students. We want our students to be able to go out and benefit the world through the skills and the approach that they take, and also the things that we work on. We think very much in terms of how this can provide a benefit to society at large, to the entire world. And that is a driving force in terms of the types of things that we work on and what we want to accomplish here at the university.
And Sam, I'm curious, have you seen this philosophy come to life in your experience at the university and your experience in this project?
Absolutely. I think when I first started on the project, Dr. Mazzeo came to me and gave me this prototype he wanted me to build, and I hadn't ever done anything like that before, and it was an amazing opportunity to get to jump in there and start making something work, within this amazing vision of saving water and making the world a better place through improving agriculture. And as he said as well, it's been a great opportunity to work with other experts and engineers in other disciplines. The knowledge that we've been able to gain from collaborating with some of the soil scientists and environmental scientists at BYU has been incredible, and it's really illustrated how much collaboration is needed. I mean, if you think electrical engineering is complicated, try learning about how complicated soil is. We definitely are really lucky to have some amazing soil scientists that we've worked with.
Of all the problems that the team could be working on, why water? Why agriculture? Why irrigation? What makes this such an important challenge to solve?
Well, if you live near the Great Salt Lake, you're probably pretty aware of the fact that the lake is drying out, and because there's different heavy metals, including arsenic and things like that, at the lake bed, that when the lake level lowers and the lake dries out, then that stuff gets picked up and gets blown around as toxic dust clouds. So I think maybe more than most people, have a really, really clear demonstration right local to us that conserving water is hugely important, and a huge amount of the water that would be going into the Great Salt Lake and keeping its levels maintained and keeping those heavy metals covered up is currently being used in agriculture, and could maybe be being used much more efficiently as we've discussed. So I think for us, it's a very local problem as well as a problem that can scale to really global impacts.
Feeding the world is definitely one of the large problems that face society at large, and doing that with limited resources efficiently is certainly something that we hope will be adopted, so that way we can solve one of the major challenges. It's amazing how much food insecurity there is even in the 21st century.
Brian, I've heard you use a really powerful phrase. You said sustainability is about your grandchildren's grandchildren, and that really helps it hit home. What does that mean to you in the context of water and agriculture? Can you talk a little bit more about the important need, for change in this area?
I want my grandchildren's grandchildren, so to speak, to be able to have a good quality of life, to be able to have the resources that they need to not only just eat, but to be able to thrive. And I think it's interesting for me personally when I think about even some of my grandparents, and they were actually kind of laborers in fields, and to think about the human part of agriculture and what it means for people to have a livelihood as well as to have opportunity. And so when you think about production or agricultural production, it's not just about how much food can we produce for how much money or resources, but it's about the people that are involved in that enterprise. And I think that by giving people tools that they can use to do that in ways that are sustainable for generation after generation, that makes a huge difference in terms of our ability to then sustain people and culture across our planet.
I mean, it's no exaggeration to say that water is our lifeblood, right? And I'm curious for, and either one of you can feel free to answer. You know, can you help put the water scarcity challenge into perspective for people who may not live in your region, right? But just like you said, this is a global challenge that you're looking to help solve. Can you help us understand how deep this issue goes?
Well, we know that across the world, irrigation practices vary, but broadly, irrigation in agriculture is a huge component, especially in typically drought-stricken areas. It's a huge component of the total water usage. In fact, it's interesting to look at the popular dialogue today talking about different sources of water consumption. And in fact, typically we'll be talking about, if you're talking about AI data centers, for example, that we might be looking at a maximum consumption of 1 or 2 or 3% of the sort of water budget that's available in drought-stricken areas. And then, in contrast, dozens of times that is being used for agriculture. So it's of tremendous importance. If we can save water in agriculture, we free up a huge amount of flexibility in using our water productively and conservatively in other ways, and making sure that we're using that limited resources, as you said, that our lifeblood, in a way that is most beneficial to everybody.
In the West, was it 40% of water is used directly, basically, in agriculture, and you start seeing the millions of gallons that are being used. You can get 1 million gallons in a single field. Yep. When you start having thousands of fields, you have billions of gallons, right? Those numbers are staggering when you think about how much water that is, and it is flowing through our river systems.
And Sam, I wonder if you could help make that tangible, like how can you make that, relatable, what millions and millions and millions of gallons really looks like?
Absolutely. So across the United States, our estimate is that about 10,000 Olympic swimming pools of water are not just used, but are wasted every day on fields that could be being irrigated more efficiently, but are not.
I mean, that really does help put it into perspective and very, very practical terms. So let's get to the project, right? So how did the Smart Stakes project get started? Was there a particular moment or a conversation that made you think, hey, this is something we really want to try to solve?
Basically, this project started because we identified a gap. And that gap was between what can be done in precision agriculture and what knowledge we need to do what needs to be done. So with our GPS technology, we can put seeds, water, all these things would basically meter precision on fields. But when you have fields that are kilometer scale, the question is where and when to do those things. And what was missing was a technology that could do this at low enough cost with minimal interference to farm operations, and the ability to help a farmer or manager to make decisions that would allow them to use resources more efficiently. That gap is what we wanted to address directly with this project.
Without data, farmers are forced to choose between basically over irrigating or risking crop stress. And so overly cautious decision making just kind of becomes a default, like out of necessity. How does better sensing change that?
farmers want to avoid crop water stress as much as they possibly can. But because of the large areas that we're talking about, as Dr. Mazzeo mentioned, kilometer scales, it's just not feasible with any currently available sensing methods to capture the variation on a spatial scale that happens within a given field. So if you picture the typical center pivot irrigated field in the United States is something like 100 football fields roughly, or maybe 200 football fields in area. And the majority of farmers will either not do any sensing at all, or if they do any sensing, they might put one sensor in that whole area. And the result of that is that you might have 50 football fields that are under irrigated and 50 football fields that are over irrigated, even if that's just as simple as a sort of half split. But in reality, we find that in that given area, we might have 5 or 6 different really distinct zones that need really different amounts of water. But as you said, irrigating all of them the same means that many of them are being underwatered or overwatered.
Simply, there's just some sensing you can only do if you have a sensor in the ground. And that was what was lacking. All these other methods were great, but sometimes you just need a sensor in the ground to be able to tell you what you need to know.
Can you describe to us what the Smart Stakes project is and what it enables?
The Smart Stakes project is about high density, low cost sensing to enable decision making. That's the goal of what we are trying to do. The project is funded by the United States Department of Agriculture. And in particular, we are looking at water because it is one of the most important inputs. But the approaches that we are taking to gather this data, this high density data, allows us to also look at potential applications in the future where it's not just water. We're looking at other important nutrients that are in the soil and being able to do this in a real-time spatial manner so that way these decisions can be made.
What results are you seeing when you're able to deploy these devices in the field, and what do those results tell you about the potential impact of this work?
Earlier this year, in a farm that we were deployed to, an actively farmed field in Utah, we were able to convince the farmer that with our system of sensors, we could do some of our own irrigation prescriptions. So he had a default value of how much he would irrigate the entire field, and it was consistent across the whole field. It was uniform. It was something like 1.5 acre inches he would do every irrigation. And to give you an idea, an 1 acre inch is about half of an Olympic swimming pool. So this is quite a lot of water that's being applied. And what we found through our sensors is that most of his field actually was being irrigated about 40% more than it needed to be. So we divided the field up into sections, and we had control sections, and then our test sections where we irrigated the amount that we thought was actually needed based on what our sensors had told us. And just for one of these sort of pie slice shaped sections, because it's a circular field, we estimated that per irrigation we were saving something like 90,000 gallons of water, which is about the amount that the average person uses per year. And when you multiply that by the 9 field sections that we have, and by the 10 to 15 irrigations that you would have per year, we're talking about, almost a whole community's worth of water usage saved in a year in a single field. And evaluating after the fact, we found that there wasn't any meaningful difference that we could detect between the control sections and the tested sections. So we saved this water functionally at no cost to the farmer and no cost to the productive output.
What I think is amazing is that a farmer basically controls their water using a smartphone now. I mean, that's basically how easy it is. And they can basically dial up or down the water, and they are controlling tens and tens of thousands of gallons of water. It's amazing. And so we are able to just give them a pretty simple, you might want to go up a little here, a little down here. And that, as simple as it is, can translate into these tens of thousands of gallons of water.
And I'm wondering too if we can maybe extrapolate out, right, and kind of think through what could be possible at a larger scale if these solutions and are deployed more broadly.
Water law in the United States is very complicated, so it's kind of a use it or lose it kind of situation. So what happens with a lot of farmers is they expand their acreage and use about the same amount of water overall per farmer or per kind of area that they have. So what you see is kind of an expansion, depending on legislation, policy making, those types of things. You could effectively probably produce a lot of the same yield with less water, with a significant percentage less. And that has huge implications in many areas where drought is a serious concern. In particular, here out west, drought is a huge item, because it's not only that we use water for agriculture, but it's also power generation. And there are other areas in the world where this kind of what we call kind of food, water, energy nexus kind of occurs, where it's really choices about how to use these resources. And so having the information about what you do in your agriculture, and to enable farmers and others to make better decisions, not only individually, but in aggregate, can have huge changes for how we think about and how we use the resources that have to be shared among all the different users of these precious and finite resources that we have.
One of the things that Dr. Mazzeo mentioned earlier was this idea that we're opening the gates to a whole different to many different kinds of sensing that could be done using this underlying platform. So that, for example, you could do fertilizer detection, or basically the idea is that you could detect all the different things that are going on. You could detect the nutrients that are in the soil. You could detect the CO2, so the plant respiration that's happening, and you can build this very site-specific map of what's going on in the soil. And we know that there are farmers in the world who take a very spatially specific approach to their farms and know their farms really well, and have been able to significantly, increase yields and farm more efficiently and be a better steward of keeping the soil healthy and alive and sustainably farmed for future generations using this high spatial density approach. But currently it's just not approachable, or it's not practical for many farmers, particularly in the United States and in other areas, to take that approach. But the dream with this technology would be to see that in 10 or 15 years, it's opened the gates to farmers all over the world being able to cost effectively and practically implement this kind of sensing approach that allows them to be much more productive and much more efficient users of the resources that they do use overall.
And Sam, I'm wondering if you could help us understand how you arrived at the technical solution behind this. So you've said before that people thought you were a little crazy for looking at Bluetooth technology for this kind of field scale sensing. What made you take that leap?
So Dr. Mazzeo was the one who actually originally made the decision back in, I think it was 2020 or 2021. But what they did is they had this solution in mind. They said, we want to be able to get the sensor out there into the field that's cost effective and power efficient and all these things, and can actually get its broadcasts from where it's at the ground to where it needs to be, to where the farmer can use it. And they did a comparative analysis and found that Bluetooth was the best candidate for all of those. For all those different parameters that they were working on, and that's what they ended up choosing. And in particular, one of the reasons why Bluetooth was chosen was that it has such huge industry adoption already, and so much development and industrial innovation has gone into Bluetooth being developed to the point where you can get these really, really cost-effective super scalable chips. The same exact chips actually that you would use in a pair of Bluetooth headphones are the ones that we're using. So that same effort that has made them, absolutely ubiquitous throughout the rest of the world and IoT devices is what has enabled them to be useful in our case.
Well, we saw an opportunity, and we weighed some different options, and this turned out to be a very good opportunity for the development of Bluetooth devices, especially in this kind of long range and very harsh environment. There was a lot of things that we looked at, and in particular, we were considering how to get a lot more gain out of the receivers, so that way we could actually do these kind of communication strategies. But yeah, we used a lot of the parts of the standards of Bluetooth that probably most people don't ever look at, in terms of how we can manipulate things so that way we could actually get these broadcasts to work in these aggressive environments.
You've mentioned that the platform that you're developing could apply well beyond agriculture. So once you have this dense sensing over kilometers, what other kinds of environmental or scientific questions become possible to study?
Once you have the ability to get information, spatial information over the kilometer scale, then you can study things that no one thought it was really possible to study before. Perhaps one of the strangest things was the paleoclimatology. When I had a colleague that came to me, it was like, well, you've got this wonderful technology. Could you use it to study carbon dioxide in soils and at depth and over really, really large scales? Because normally they would only dig one pit and had one sensor, and they'd have to extrapolate over huge areas. And instead, we're able to use a platform like the one we have to start looking at these type of studies that were just simply impossible to do in a cost-effective way in the past. And so the ability to gain information over large areas and do that in a cost-effective manner truly opens up studies for many different aspects of climate and geology and different environmental processes that are going on all over the world.
If you've been on a hike or a walk, you can definitely see how much the environment changes around you, even on a scale of like a few meters. And when you think that, if the average geologist or climate scientist or environmentalist or plant scientist or what have you might be trying to do science based on maybe one sensing station or something like that every several kilometers, you can imagine how much detail we're missing and how much data is not being captured. We're basically guessing at a huge amount of the things that we're trying to measure because it's just been infeasible up until now to actually detect things at a scale that is more reflective of what's really going on. So there's just so many questions across those different fields that would be wonderfully suited for applications of this sensing technology.
We've had interest from other groups. Actually, even the spatial technology, people are like, well, can you put this on a lake? Can we do studies where we're now getting information from, large water bodies? And the applications for spatial sensing in ecology are practically limitless, because they would love to have this type of technology readily available to put whatever sensor that they want, and now be able to get that information communicated to pretty effectively. I mean, there are cellular solutions for some of these things, but usually it's just not very cost effective to do it at these large scales. Whereas having the Bluetooth, being able to just broadcast it, just brings down the energy required and the kind of ability to aggregate all this information much more easily.
There is the technical learning, of course, but there also seems to be something much bigger. And, the idea that students realize that they can help solve global problems. What do you hope students take away from participating in a project like this?
Students in a project like this get to dream and actually build the solutions that can change the world. And they don't do it in isolation. What I love about this project is we have students from multiple departments, not just electrical engineering. We have students that are studying in geography, that are studying in plant and wildlife sciences, and they come together, and they have never worked together on a project like this before. And they share their experiences, they share their abilities, and they start to realize how important it is to build effective teams to tackle these types of problems. That's like an unmatched experience when they get to do that. And I think that they come out with a confidence and set of skills that allows them to be very effective in whatever career path they may choose from this point onward. And for me, that's really exciting, because what we really want is we want students that are capable of tackling some of the biggest challenges that the world has, and to learn to do that in teams. That way they can actually come up with solutions that people can use.
And Sam, from your perspective, what has this project meant for you professionally, personally? Has it changed how you think about the kind of work you want to do?
Absolutely. I had never thought about maybe the altruistic impacts of what my career might be until this project. In fact, I had never had any idea that I might get involved in agriculture or anything like it. But reflecting on it now that I've been part of this project for a few years, I don't think I can go back. I'm now at a point where it's become so important to me that the research that I'm doing is something that I genuinely believe will benefit the world and make it a better place. And not just that I've had the opportunity to get used to that mindset, but also the fact that like I believe that it's going to work, and I think I've been kind of empowered by this idea that little old me working away at this project for a few years, and when I first started, I didn't know anything, and I just only know slightly more than that now. But based on on my efforts and the few people around me and my professor, we've been able to make something that might be genuinely transformative.
The passion that both of you feel about this project and the challenge that you're solving, just comes screaming off the screen, and it's really inspiring. At the same time, a problem like water scarcity isn't something that any one group can solve on its own. You've got researchers, you've got farmers, you've got industry partners, even policymakers are playing a role. So can you talk about the importance of collaboration when it comes to solving problems like water scarcity?
I would never have approached this without having some excellent people that I was working with. And Neil Hansen, in particular, Ruth Carey, these are experts that have been studying the problems for decades. That's what was one of the things that I didn't realize was how important it was, and how they were saying, in 2000, we wanted a solution like the one that you're building now. And so they've been waiting and wanting these solutions so that way it enables them to bring these ideas, to bring these solutions out to the real world. And so that is an amazing experience to be part of a team of people who they're already passionate about what they're doing, and we're giving them tools that enable them to actually realize that vision. That's an amazing experience for us to be part of.
Well, I mean, the foundation of this whole project is Bluetooth, and as far as I understand, you're here representing a collaboration between many different entities to make a shared standard that can be useful for that. And just the fact that it's such a mature platform that has had so much thought and energy put into making it something that can just work for people, no matter what the situation that they're using it in is, has been absolutely huge for us. And furthermore, within the scientific community, I can't tell you how often I'm looking to solve a particular problem and will end up consulting literature from other people who have already tried to solve that problem. And, maybe in their particular case, it wasn't something that ended up with a super specific application, but because they did that legwork and took the trouble to publish their results, that's now something that can benefit our project and help us get our message out there, I guess, and get our research complete as well.
I appreciate your nod to Bluetooth's own origin story and our mission of standardization. So how could farming look different, 10 or 20 years from now?
That's a great question, but I think what would be amazing to see is that farmers don't really have to guess anymore in the same way that they do now. They can go into situations with a great deal more confidence. I know that one of the things that we've done technologically in the last few decades that's helped farmers enormously is that our weather forecasting is improved, which enables them to make decisions that are wiser and are more environmentally conscious. And I believe the same thing will be possible with high spatial density sensing. We'll see farmers that are only applying exactly as much fertilizer as is needed for every particular area of the field, and that way they're not encouraging, harmful growth of weeds that don't need to be there. They're not overtaxing the soil and overusing the soil to the point where it's not biologically viable after a certain number of generations. Basically, they're creating a sustainable, repeatable process that they can use so that the benefits of their work doesn't just transmit to them and to the market right now, but is that something that their grandchildren's grandchildren are using also.
What I see as transformative in 10, 15, 20 years is the use of the spatially dense data to make decisions. I think it will be enabling for so many, and not just water, not just the resources. And to some degree, it kind of is like going full circle. I think that really a farmer's relationship with the land is actually very personal, and it's small. And to some degree, we've the farms that we now have with that, they're just so large. It's almost impossible to really see the scale unless you're like flying over it. And in a sense, we're going back to understanding what happens in a very small plot. And yes, we're replicating that thousands of times, but it's like we understand then what happens at a very small, intimate level where the farmer could really think about and interact with a small section of land to make it productive and to make it efficient and to make decisions that are long term about what's best for that land and what can be produced from it. So it's exciting to kind of have both scales. Like it's small and what's going on there, but it's also large because it's the ability to then do that on the scale of thousands and thousands of acres. And so that's exciting to see what potentially could transform the way that we do something that has been done for thousands of years.
One of the things that we'd love to see as well is that these technologies become available around the world. And I think the fact that they're so low cost is part of what will enable that to happen. A huge hope for this project is not just to see that the same farmers that are already, technologically advanced and already using some sensing get more sensing, but that farmers who would never have done it before, even in the United States, where 80% of farmers don't use any kind of moisture sensing, adopt that as well, so that it becomes something that's being used everywhere and not just in a few cases.
And I should add that it may not come from us. We're actually completely open to the fact that by showing what is possible, we hope other people also are part of that conversation and part of the development, so that way these solutions can spread across the entire world. Even if this is not successful, what the students have learned is a success. And I see Sam as a success. I see the other students on this project as a success. And no matter what happens with the project, they are successes. And I truly believe that working in this environment on this project is launching them to do great things. And they'll solve other problems that we don't even know exist, but they will have the skills and the ability to go out there and really make the world a better place. It really is a benefit to the world to have the opportunity to work with students and give them these type of opportunities, so that way they can develop what they need, so that way they can tackle things for the rest of their lives.
So many passionate people all over the world are working on problems like this. We go to research conferences, and everybody there is basically, their life's work is to try to make the world a better place. And it's not always necessarily because academia is the most financially incentivizing field, but it's because they really believe that things can be better. And seeing how much expertise and insight and effort is being put into that is hugely inspiring.
Brian, Sam, thank you both for joining us today. I have to say one thing that kept jumping out to me was how often you came back to people, whether it be students, whether it be grandchildren's grandchildren. We talked about water, we talked about agricultural sensing technologies and research, but the focus has always come back to students, farmers, communities, and future generations. So just this idea that some of the world's biggest challenges are not out of reach, that there are problems that are, worth working on, and that we can all play a meaningful role in solving them. That's just, it's so refreshing and honestly, pretty inspiring. So thank you for the important work that you're doing. Thank you for sharing it with us today. And, best of luck to both of you. We'll be excited to see where the project goes next.
Thank you. Thank you for giving us an opportunity to talk about it.
Thank you so much.